Welcome to the Matroid Learning Seminar. So we're following Oxley's book, Matroid Theory. And I'm going to start with chapter 1, what is a Matroid? Chapter 1 is rather long, and it will probably take us about half the semester to get through chapter 1 itself. But we're doing it in a very thorough manner. So we're paying attention to all the little details. So definition. A matroid M is a set E of n elements and a family I of subsets of E satisfies. So it's a very set theoretic definition. And matroids in its absolute generality is basically a set, a collection of subsets of the set that satisfies certain properties. The empty set is in this special family script I. If I1 is an I and I2 is a subset of I1, then I2 is an I. And 3, if I1 and I2 are both an I, very soon I is going to be called independent sets, and it will make sense for that symbol script I. But right now it's just a collection of subsets. If I1 and I2 are members of I such that I1 is less than I2, then there is an element E in I2 minus I1 such that I1 union E is in I. So this is I1, this is I2. May intersect or may not intersect here, right? So there'll be an I1 and I2, I1 is smaller than I2. You'll find an element E here such that you can grow I1. And that language comes from linear algebra, growing independent sets. Can grow I1. So note, we write M in this manner. We say E comma I to denote the matroid. And when the context is clear, it's just M. E is called the ground set. Three, members of I are called independent sets. But the motivation for that terminology is still not there. I see. Welcome to those who just joined in. We just began. Matroid is a set system. It's got a set E and a collection of subsets that satisfy certain properties. And we're listing out the properties here. And there are 3 properties, and we're just in terminology still. Independent sets. And the motivation for why this is called independent sets will happen in a little, it will be clear in a little bit. And these three axioms are called independent axioms. Independence axioms. So for our first example, it's not going to be graphs or matrices, which are, the typical examples given of a Matroid. Our first example is just going to be a set system. So E is the ground set is just 4 elements. And let's consider various collections of subsets I and see if they satisfy the properties. So if I1 is, for example, the empty set, which has to be in it all the singletons and all the pairs. So I'm going to list all the pairs. Okay. So would this satisfy the axioms? First one is satisfied, right? Second one is also satisfied. I won't put you on the spot and make you all answer questions. And the third one is sometimes a little bit harder to check, but in this case, because every pair of elements is in this collection, this flagged collection, number 3 is just satisfied in a relatively simple manner. So this is a Matroid. So E with this collection of sets is a Matroid. Now let's think about how we would represent such a Matroid in a pictorial manner. We are limited in the pictures that we can use. We can use them, if they're graphs, of course, we can use pictures. And if they are not graphs, then we're limited to maybe 4-dimensional Matroids. And this is small enough that we can think about how to visualize it. There is some debate in the Matroid community whether it should be the graph notation should be introduced first or the geometry notation should be introduced first. And the reason is it's actually very hard to switch the thinking from the graph notation to the geometry notation where you have points and lines in the plane. So I'm actually going to take a bit of a risk here and introduce the geometric notation right away, which is several sections into chapter 1 in the book. So we want to somehow express that this collection of independent sets, right? And in a geometry, if you have 3 points on a line, right, then those 3 points are dependent. They're in the geometric sense, which will become clearer later. But here, if there are just 2 points on a line, then they're independent. So since the singletons are independent and the pairs of points are independent, this is one way of representing this Matroid. This is a geometry, as in points and lines, not graphs. And these are lines, the rules being 3 points on a line represent a kind of dependence relation between them. And there's always a pair, there's always a line that passes through any 2 points. So this is an entire section and it comes much later, but I thought I would just throw it in up here just so as to get comfortable with both the geometric and the graph theory notation. After all, in graph theory also we have points and lines, and that's why I specifically sort of extending the line here a little bit to indicate this is not a graph, this is not a path. So points and lines in the plane. All right, So let's talk about this one. It's got all the singletons. And all the pairs. So let's just write that down, all the pairs. And all triples. So the only thing missing here is the entire set 1, 2, 3, 4. So all triples that look, what are the triples here? 1, 2, 3, 1, 2, 4.
Can I interrupt you? You use
Sure.
you use plural lines. So are you thinking of these subsets as segments, or is that just the single line and these are subsets of that line?
Yeah, so I'm thinking configuration in the Hilbert sense. When he wrote his famous geometry book, he has a chapter on configurations, and his definition of configurations is slightly different, but that's what I'm thinking. Projective geometries, projective plane, points and lines in the plane. That's what I'm thinking. Make sense?
But, well, maybe not yet, because from my point of view, whether you're in the projective plane or the Euclidean plane, I only see one line singular and you have an S on the end.
Maybe I introduced this too quickly. This is the uniform Matroid U24. I don't know if that rings a bell. Maybe I introduced it too quickly, and there needs to be careful introduction of points and lines in the plane. So yeah, maybe I'll elaborate.
So, I mean, are you saying that the line determined by 1, 2 and the line determined by 3, 4 in the picture, they look like the same line, but am I supposed to think them as two lines? Is that what you're saying?
No, it's just one line. So it's if you have a bunch of discrete points in the plane, every pair of points determines a line, right?
Okay.
And so it's just one line that passes through 1, 2, 3, and 4.
All right.
Yeah.
Thank you. Sorry.
No, that's very good. It's the geometric representation, when we also have the graph representation, is actually one of the hardest parts of Matroid theory. So so here we have all triples, and once again they satisfy the 3 Matroid axioms. The empty set is very much in it. It's every pair of points, all the triples. So they satisfy 2 and 3. And now again, there's some kind of independence concept here, that how would we depict it on a plane, for example? It is 3 non-collinear points on a plane, just from geometric perspective. 3 non-collinear points determine a plane. Sort of, there's some kind of independence concept there. And a fourth one is going to be dependent on those other three. So in this case, one way of visualizing this could be 1, 2, 3, 4. 4 points scattered on the plane, no 3 on a line. So you pick any 3 points, they determine the plane, and that's the concept of independence here. And then, of course, we have the whole thing, right? Will be the empty set, the singletons, all pairs, all triples, and 1, 2, 3, 4 also. So this is actually a family. It's called uniform matroids. And in general, let E be 1 to N, the points we're talking about, and let I be the set of all subsets of size less than or equal to R, and R should be less than or equal to N. Then I will satisfy 1, 2, 3. And this matroid is called the uniform matroid URN. So this was U24 over here. This was U34, and this was U44. And these uniform matroids are very, very important for coding theory. And there's a number of unsolved conjectures on them. Just really fascinating objects, very simple to define, and yet there's so much there in this class of matroids. So for our second example, we're going to look at a matrix. All right, I think everybody's going to be more comfortable with this one. It's a matrix, but it's a matrix over a finite field, not real numbers. So this is going to be my matrix. And this is a matrix over the finite field F2. So one thing that makes matroids have a bit of a learning curve is that we right away, I see there's two people in the room. Welcome. Sorry, I'm not going to have a waiting room after today. Maybe I shouldn't even have had one today. I hope you all didn't wait too long. We did the independence axioms, and we're doing our second example. So you kind of came in at the right time, because the second example doesn't depend on the first one. All that it depends on is these three axioms over here, which I will grab and pull down. So a matroid is a set and a collection of subsets of the set that satisfy these three axioms. And as we go through the second example, these axioms will become clearer. In fact, the second example is the embodiment of the independence axioms. Okay, so one of the things that makes matroid theory a little bit tricky is that we've gone straight to finite fields, but it is linear algebra over finite fields. So it does help to have an abstract algebra course. However, you will see that we don't use too many things about finite fields, just the basic finite field arithmetic, at least for the binary field, right? This is F2, this is the binary field. The elements are just 0 and 1. So if you're hearing finite fields and thinking we didn't do that chapter in algebra, this for the students, then don't worry, okay? It's as long as you know binary arithmetic, you'll be fine. So we're doing a linear, sort of a linear algebra on finite fields, and Whitney's original paper in 1935, which sort of introduced the word matroid and all of the stuff that we're doing today, pretty much. He considered matroids over real fields. Subsequently, matroids over finite fields is a very, very rich field of, no pun intended, rich topic, and with lots of conjectures and results very similar to graph theory. And therefore, the current thinking is to introduce finite fields right away. So what we'll do is we'll label the columns, right? So we're labeling the columns, and the ground set here, the set E in our definition, will be 1, 2, 3, 4, 5, 6, and 7, right? And this, this matrix sort of is the columns of this matrix come from a vector space of dimension 4, right, over F2, though, not over the rails. So I consists of the independent sets in the linear algebra notion of columns of the vector space of dimension 4 over the binary field. So that's the notation we use, dimension 4 over the binary field. So it's not R4, which is, it's not R4, but it's a finite field. But the arithmetic and the concepts of independence carry over from your typical, Rn straight over to the binary fields and actually all finite fields. So let's look at what the independent sets of columns would be over here. So what would it be? It would be empty set is independent always by definition. The singletons here, they're independent. There's no column of zeros. That would be something that's not independent. Right? Then all pairs of columns, if you check, except 1, 7. Right, so what's the story with 1, 7? Well, if you add them up, what do you get? 0, right? 1 plus 1 is 0. I just realized I should keep track of the time. Yeah, so if you add up these two columns, 1 and 7, you get 0. So that's not independent. And then let me grab I got some figures here. It does help to have a computational perspective to play with lots of examples. So if you have to think about what are the independent sets of columns here, it's not practical to compute anything in this area by hand. I mean, you could, but you can use software to get it. So these are all the triples. We said all the pairs except 1, 7, then all the triples, and then all the 4-element subsets. And if you were just using a program to check independence, you'll see that 5 and 5-element subsets and higher won't be there. This matrix has rank 4, but then we're again jumping ahead a little bit. So let's just stay with a tedious computation of what is independent and dependent that we can just hand over to the computer and say, okay, the computer told us these are all the independent sets. Having said that, the next thing I have is rank. I do bring up rank, but there are rank axioms. Rank axioms come later. So in general, let A be a rank R matrix.
So can I interrupt you again and ask you
Sure,
whether
sure.
So the first four columns are an identity matrix.
Mhm.
And so is there some method by which the next three columns were chosen, or?
Yes, actually, in this particular example, this is also a graph. So as soon as we do the graph example, and you see the picture or the graph expression of this Matroid, it'll become immediately clear as to why these were selected. So, for example, the 1, 2, 3, 4, 5 is 0, right? If you add up columns 1, 2, 3, 4, 5, you'll get 0. So 1, 2, 3, 4, 5 is not independent. We still haven't talked about what dependent is. So we'll just say not independent here. So this is not in I, right? And then so in the and 1, 1, 7, not in I. And not every 4 element set is independent either. For example, 1, 2, 3, 6 is not in I. And then this will actually become in about 15 minutes. This will be the graph. So it'll be 1, 2, 3, 4. Right, 1, 2, 3, 4, and then 5 will be this, 6 will be 1, 2, 3, and then 7 will be parallel to 1. But that'll happen in a moment. So I did choose this example carefully, so it will also have a graph expression. And but at this stage in the development, it's just, there are sets in I, and there are sets that are not in I. And these sets that are listed over here all satisfy those independence axioms. And number 3 here is not obvious, but it's actually quite a simple, beautiful proof. And that I will do right now. Is this okay, Joe?
Yeah, thank you.
Yeah, you're welcome. And so in general, let A be a rank R matrix in the linear algebra sense, written in standard form. If matrix is not in standard form, you can do elementary row operations and bring it in standard form where you have the identity on the left. And again, the sentence that I just sort of rattled off needs several examples to totally understand it. But let's take this as the format that we want our matrix to be in, after we have taken some arbitrary matrix and done elementary row operations, thrown out any 0 rows, etc. And let E be the set of columns. So these are the columns. So the column labels are going to form the ground set. And let I be the set of linearly, I'll throw that word in, linearly independent sets of columns in the vector space V4 in any field, not necessarily finite field, not necessarily real number, it's just any field, right? Sorry, not 4. What's our rank here? VRF. Then this is our first sort of claim. EI is a matroid. So let's examine this, all right? And all this needs is knowledge of linear algebra 1. But if you look in any linear algebra 1 textbook, you'll find this little portion that I'm going to do now as a prelude to the singular value decomposition. and the SVD theorem. And what happens is there's not enough time in a typical linear algebra 1 course to really get that far. Sometimes you can. And therefore, this little piece is not covered, but it could be covered in a linear algebra 1 course. So why? Let's examine the axioms. So for those who came in after we started, these are the 3 axioms. Let's bring that down. So the empty set, by our understanding of linear independence, is in I. And if I1 is an independent set, right? And I2 is a subset of independent set, I1, then I2 will be an I, right? It's just linear algebra there. So the only thing that needs examination is number 3. How do we grow a linearly independent set? And the intuition there is that you can take any linearly independent set and grow it to a basis. So that idea is what's encapsulated in axiom number 3. And it was Whitney's genius to recognize these 3 axioms as axioms that lead to a meaningful system that gives lots and lots of examples. So let's prove 3 for matrices. Let I1, I2 be independent sets of columns such that I1 is smaller than I2, right? Let W be the subspace of the vector space spanned by I1 union I2. Then dimension of W is at least as big as I2, right? As the size of I2. So suppose, if possible, right, we're headed for a contradiction. Suppose I1 union I2 is dependent for every E in I2 minus I1, right? So a little picture here. Here's my E. And I1 union E is dependent. Then W will be in the span of I1. And dimension W is going to be at least I1, less than or equal to, said that wrong. Dimension W is less than or equal to I1, at most I1. Therefore, you get I2 is less than or equal to I1, and that's a contradiction because we specifically chose I2 to be greater than I1. And the whole proof can be encapsulated in the idea that an independent set of vectors can be grown to a basis. Even though we have not defined basis as yet, but there is the notion of basis in linear algebra. So if you have an independent set and it's not the maximal independent set, then you can grow it. So this is what we call a vector matroid. And it's written MA like this, or MA depending on what you see. So, so as in the matroid that can be expressed as the matrix A. Sets in I are called independent sets, and now the reason for that terminology is clear. And axioms 1, 2, and 3 are called independence axioms. The reason for that is clear. All right. Any questions so far? So for the students in the audience, it's so far it's just linear algebra, but it's a spin on it. It's a perspective on it. So so if you're like maybe trying to still wrap your head around it, you know, that's normal. You'll get used to it. So it's like it's all the usual words, but there's a perspective put on it. So a subset of E that is not independent is called dependent. Finally, defining dependent as you would expect it to be, defined a minimal independent set is called a circuit. Bit of a notation clash here. Circuit in Matroid is the same as cycle in a graph, but in graph theory, circuit means something else. So that's something to keep in mind. I just wish that this was called cycle instead of circuit, but the notation appears to be fixed.
Do you mean dependence, minimal dependent set?
Yes, that's what I meant. I wrote independent. Thank you. Yeah, minimal dependent set is called a circuit. Maximal independent set will be called a basis. That's going to be the next section. So what is minimal? First thing is, what does minimal dependent mean? Minimal in Matroid theory means C is dependent, but for every E in C, C minus E is not dependent. So here it'll be independent. So this, so whenever you see minimal, this is what it means with, you know, different terms involved, but the object is blah, and you take out one element and it's not blah. So we already talked about dependent sets in our previous example. For 1,7, we kept calling it not independent. Now we have a name for it. 1,7 is dependent. And then, but we want to look at minimal dependent sets, right? So let's grab this matrix again. There's fewer minimal dependent sets. We'll use script C for obvious reasons, and let me add a few more pages here. I should have a page here. Okay. Script C is 1,7. We talked about that several times. 1,7, 4, 5, 6. They're all minimal dependent, like 4, 5, 6 is here. 4, 5, 6. You take out 1 and it's going to be independent. And we saw that all pairs except 1,7 is independent. What else? Little bit of calculation needed. 2, 3, 6, 7. 1, 2, 3, 4, 5. And this is actually doable by hand if needed. I think this is all of it. So let's look at example 1 again. Example 1 was URN, right? The uniform matroids. So E was 1 to N, and that I was every subset of size less than or equal to R. So what would be circuits? Minimal dependent. Everything less than or equal to R is independent. What would be dependent? What would be dependent is everything strictly greater than R. So the minimal dependent would be all subsets of size. Anybody wants to chime in? R plus
Plus
one.
one.
Yes, very good. Yeah. So those would be the circuits. And this brings us to the circuit axioms. The circuits also satisfy what we call circuit axioms. And in this sense, a matroid is very much like a topology. It's got multiple different cryptomorphic axiom systems. There's 13 of them. And within them, there's like, I don't know, 40 or so variations. Not to worry, we're not going to be doing all that. Although that is actually, nobody wants to do that. So if someone really gets into the cryptomorphic axioms of matroids, you could probably get at least one paper out over there finding some new cryptomorphic axiom system. But yeah, we're just going to do the main ones. So this brings us to the, Rebecca, I see you raised your hand. Go ahead.
Yes, what are cryptomorphic or tryptomorphic? I'm not sure what word you're saying, axiom systems.
Yeah, cryptomorphic. Those are equivalent. It's a fancy word. As far as I can tell, it's a fancy word for equivalent. And so the circuit axioms and the independent set axioms are equivalent. You can go from one to the other and vice versa. And topology has a lot of cryptomorphic axiom systems. Okay, so just a fancy word for equivalent. So here's our first proposition. Let EI be a matroid. How are we doing on time? And C be the family of minimal dependent sets. Then C satisfies. The empty set is not in C, as you would expect. The empty set is independent. If C1, C2 are circuits and C1 is contained in C2, then C1 is equal to C2. Okay, and the third one, the first two are fairly obvious, as in think cycles in a graph. You can't have one cycle contained in another, right? So if you have one cycle contained in another, then they're equal. And the third one is if C1, C2 are circuits and E is in the intersection of the two, then there is another circuit, C3, such that C3 is contained in C1 union C2 minus E. So it's called the circuit elimination axiom or something. So here you have C1, C2, and here you have an entry in the intersection of C1 and C2. Then C1 union C2 minus E contains a circuit. Sometimes it could be a circuit, but the axiom says it contains a circuit. That's all that's required. So in the interest of time, we'll actually skip the proof of this proposition. And before I post these notes, I will actually insert the proof. It's I want to try to stop on time at 5. I don't want to subject you all to more than an hour of this. And then I will just fill in the proof before sending out these notes. And then proposition 2, and this is actually a lot of work, and I wasn't planning to do it either. The independent axioms are equivalent to circuit axioms. So one direction will follow from proposition 1, and the other one needs a lot of work. And so I want to get to the sense of Matroids, a perspective, the graphic perspective, how results are used, how results are obtained, etc. Hopefully by the end of the semester. And therefore, I don't want to get stuck on some really long cryptomorphic proofs. But as I said, nobody wants to do that. So there's an opportunity there. So let's get to the graphic example. And here I'm going to assume that you know some elementary graph theory, nothing very complicated, just what is a graph and paths and cycles, things like that. Right? So our third example of a matroid. So we have the uniform matroids, the independent, the matrix matroid, and now this is the graph matroid. Although that's not how we say it. It's like the matroid perspective on graphs. A graph gives rise to a matroid. Now, let G be a graph with edge set E and vertex set B. And then just forget about the vertex set. In matroids, we don't see, the matroid perspective of graph doesn't see vertices. They're there, but we don't see, they don't play any role. And our edge set has n elements. Usually our edge set has m elements, and n is the number of vertices. So something to keep in mind here. Our edge set will have n elements, n edges in our graphs throughout when we're doing matroid theory. So let C be the set of cycles in G. Then C.
So are you allowing loops? And I assume you allowed.
Yes.
Okay.
Yes. So that's another thing in matroid theory. It is customary to allow loops and parallel edges in the definition of graphs. And if you want to talk about just graphs without loop and parallel edges, we use the word simple graph. So yeah, this is in graph theory, we say graph, we don't allow loops and parallel edges. Yeah, so that's just a good point, very good point over there. Okay, it's always a multi-graph. If you want to talk about simple graphs, and we say simple graphs. So let's see be the set of cycles, and then C satisfies the circuit axioms. And let's take a look at this example here. This is a parallel edge. So E is 1 to 7, and C is, if you look at the cycles here, you'll see 1, 7. And in fact, if I didn't change any edges, I think this would be exactly the same as this. Yeah, these are the set of cycles. So from a matroid perspective, this matroid here, EC, you can represent by, so can be represented by a graph or a matrix. And it's the same thing. It's just two different ways of sort of visualizing the set system. And now think about the cycles. Why would C satisfy the circuit axioms? Well, the empty set is a circuit. We'll take that as a obvious. And if you have two circuits, right, two cycles, right, and one is contained in the other, then they're equal, right? So again, it's just the third thing that needs to be checked. And I'm going to explain it with an example. Let's C1, C2 be two circuits, and E is in the intersection. So we want to say C1 union C2 minus E contains a cycle, right? I use cycle and circuit interchangeably, even though they mean different things in graph theory. That's just really unfortunate notation. Yeah. So suppose you have two cycles, right? There's a cycle, and there's a cycle, and they have an intersection. This is sort of the edge that is in both cycles. Then you can just remove it and you can see the bigger cycle, right? So C1 union C2 minus E, this is E, this is C1, C2, is a cycle. But maybe you have something like this, right? And you have two edges. So this is E and this is another edge F. In that case, right, C1 union C2 minus E has F. So but it contains a cycle. So it's not is a cycle, contains a cycle. And the cycle that it contains is still, this one. But remember, as sets, C1 union C2 minus E also has F. So it wouldn't be right to say C1 union C2 minus E is a cycle. So in that case, we say contains a cycle. So if you're removing the red edge, because then the other edge is still there. And what's the proof like? The proof is just basically pretty much like what I said, except in general terms. So that's the picture, and this is the and it just pretty much says in words what I said in the picture over there. All right, it's just words. It's we're following Oxley's book. This is a picture of Oxley's book, and this matroid is called the cycle matroid of a graph. It's denoted by MG like this, as MA, MG. But the way to think about this is that matroid is a perspective on graphs. You can think of a graph as a matroid. You can think of a matrix as a matroid. And they have this, it was Whitney's genius that he recognized that graphs and matrices have this commonality. Yes, Rebecca?
Can all matroids be represented as a graph, and can
That's
all
a wonderful-
matroids be represented as a matrix?
And no. So the matroid is just a very, very general example, like URN, the uniform matroids that we did first. Even U24 cannot be represented as a graph. And in that set, you can have what we call representable matroids. Those are the ones that are representable over finite fields. Binary is the smallest finite field in that sense. And then graphs is this like tiny little subset of matroids. But the amazing thing, and this is where a lot of the research has been done, is that the Graph-Minor theorem is expected to hold for all representable matroids. That is all. I mean, matrices are such the set of all matrices is so much larger than the set of all graphs. Not every matrix can be represented as a graph, and yet the basic structural ideas that exist in graph theory carry forward very nicely to matrices representable over finite fields. Okay, not true for infinite fields, certainly not true for matroids in general. So in that sense, that small class holds all the structure and sort of the significance of the entire larger class of matrices representable over finite fields. So that was a very good question. And I'd like to end with a quote. And so, this it's as if, I mean, who knows? I'm not entirely sure what Tut intended by this. I never got a chance to speak with him. He was a bit before my time. But I mean, one interpretation could be that this is the graph and it kind of disappears and is replaced by this matrix. And you might think that, the missing something by not having the graph, but actually the matrix captures all the essence of the graph, and you can get the information out of the matrix faster than you can get the information out of graph sometimes. So thank you for joining and allowing me to expound on a topic that I really like. I will stop the recording.